Our work focused on resolving the shallow structure of the Array Basin. The structure of the Array Basin plays an important role in the seismic hazard of this densely populated area, and the existence of the basin structure could amplify the strong ground motion waves. Here, we investigate the Array Basin structure with ambient noise correlations between the 5 oil industrial dense arrays and 21 Southern California seismic network broadband stations. The dense arrays are shown in orange, and the broadband stations are shown in blue triangles. We observe clear fundamental mode and first overtone relative noise correlation functions. The left panel shows noise correlation functions as a function of the distance and stacked in distance bins. These noise correlation functions are filtered between 0.5 to 2 Hz. We see 2 clear move-out trends corresponding to the fundamental mode and first overtone relatives, respectively. The right panel shows the wave fields of the NCFs from the same virtual station LTP to 4 different dense arrays. These wave fields are far from even or isotropic. This means that the Array Basin has strong structural heterogeneities to be resolved. This figure shows the ray coverage of our data for 2 different modes and 4 different periods. We see that although at the outer rim of the Array Basin, the ray coverage is not even, the central part of the basin is well mapped and well covered. This suggests that we could potentially have a good resolution of the shallow structural model of the central part of the Array Basin. This is confirmed by our checkboard resolution test. The checkboard resolution maps for 2 different modes and 4 different periods show that the resolution for the central portion of the Array Basin is very good. So we obtain group velocity maps through the standard straight ray seismic tomography. The results is shown in these 8 figures, and the most pronounced feature for the group velocity maps is the shrinking high velocity zone as the period goes longer. This means the basin gets narrower as it gets deeper. Another feature is that the low velocity zone is surrounded by 2 high velocity patches at 2 different sites. One is the northeastern, another is the southwestern. These 2 high velocity zones are correspondent to 2 different high velocity structures indicated by the San Pedro Hills and also the Puente Hills. We also note that the basin structure is far different from the smooth. We see a lot of small-scale heterogeneities. We further derive a 3D shear wave velocity model using these group velocity maps, which covers a large portion of the central Array Basin for the depths shallower than 3 kilometers. The detailed shallow velocity structure is well resolved, and the Newport Inglewood fault is imaged as a high velocity strand at the horizontal slices at the depth over 2.0 kilometers. And also it's likely accompanied with a sharp velocity contrast, as shown in the right figure, the depth profiles. With detailed mapping of the structural heterogeneities, our model provides new constraints on the local strong ground motion predictions. Here, this is illustrated by the comparison between our model and 2 CDM models. In general, our model is more similar to the CDM-S model. However, the small-scale heterogeneities look more like to the CDM-H model. This difference is more pronounced in the strong ground motion amplification predictions, in which we use a finite difference space method to simulate the amplification of the vertically incidental shear waves. We see that our VS model, DenseTomo, produce similar strong ground motion amplitudes against the CDM-H model, but they are both much larger than the CDM-S model. This suggests the importance of incorporating small-scale heterogeneities in the hazard assessment. We further illustrate the effectiveness of our model. Here shows the comparison of the synthetic group velocity maps against the observed tomographic group velocity maps for different modes and different periods. The first row is the observed tomographic group velocities. Second row is the synthetics from our DenseTomo VS model. Third and fourth row are CDM-S and CDM-H models, respectively. We see that our DenseTomo synthetics fits the tomographic observations much better than the 2 other CDM models. The CDM-S model over-predicts the group velocities at longer periods, while the CDM-H model generally underestimates the group velocities. In terms of the directly peaked dispersion data, we forward simulate the dispersion, the group velocities for different ray paths and compare them of different models against the directly peaked dispersion curves. We see that the synthetics from our tomographic model well predict the dispersion data, while the CDM-S synthetics over-predicts it, and CDM-H synthetics under-predicts them. This suggests that our model provides much better fittings to this new rich dataset. Thank you.